Hello friends, today in this video we will learn about Pond Storage Hydroelectric Project in Indian scenario.
Welcome to this explainer. Okay, today we are exploring a truly fascinating concept. We're talking about turning massive bodies of water into gigantic gravity-powered batteries for the electric grid. When we think of energy storage, we usually picture those little lithium-ion batteries in our phones or maybe in electric cars. But as we push toward a carbon-neutral future, those chemical batteries simply aren't big enough. Instead, the real heavy lifting is going to be done by mountains, gravity, and literally millions of gallons of water. We're looking specifically at India's monumental blueprint to build nearly 50 gigawatts of this storage capacity by 2032.
Okay, let's dive into this. Now, the modern energy grid faces a massive problem. Solar and wind power are absolutely excellent, clean sources of energy, but they're inherently intermittent, right? When the sun goes down or the wind just decides to stop blowing, the power drops. But modern society demands constant, unblinking reliability. You can't just have rolling blackouts every single time a cloud rolls in. So the big question becomes, how do you store a gigawatt of energy to release exactly when demand spikes? You need a system that can respond in seconds, acting like a massive safety net for the grid.
Well, the answer to that question is pumped storage hydropower, or PSH. Think of this as the unsung hero arriving to save the renewable grid from all that unpredictability. A PSH facility isn't just a regular dam. It's literally a closed-loop battery system. It lets operators actually store and schedule hydroelectric power generation, while also playing a totally crucial role in stabilizing the grid's frequency and voltage. Unlike your standard run-of-the-river hydro plants, which, depend entirely on whatever the natural water flow is doing, PSH puts the control firmly back in the hands of the grid operators.
And this brilliantly illustrates how the mechanics of gravitational storage are actually super elegant and straightforward. Think of it in 3 simple steps. First, during hours of really low energy demand, say the middle of the night when the wind turbines are still spinning but everyone is fast asleep, the system takes that excess cheap electricity and uses it to pump water from a lower reservoir all the way up to an upper reservoir. Second, the water just sits up there, effectively storing all that gravitational potential energy. Finally, during periods of peak demand, they release that water. It rushes back down through reversible turbines, converting that mechanical energy straight back into electricity for the grid.
Now, you might be wondering, wait, doesn't pumping water all the way uphill waste a ton of energy? Actually, the round-trip viability of this system is incredibly impressive. It sits right around 70 to 80%. That means for every 10 kilowatt-hours of electricity consumed to pump the water up the mountain, a massive 7 to 8 kilowatt-hours are produced when it comes back down. When you factor in the incredibly long operational lifespan of these facilities, we're talking often 50 to 100 years, and the sheer volume of energy they can hold, it makes PSH the most proven, large-scale, and long-duration storage technology we have right now.
However, not all pump storage is created equal. Historically, a lot of these systems were on-river or open-loop, meaning they hooked right into naturally flowing river systems. But India is making a huge strategic shift toward off-river or closed-loop designs. Why the switch? Well, because connecting to rivers brings a whole host of massive complications. You've got to navigate intense environmental clearances, manage impacts on downstream ecosystems, and critically, negotiate really complex interstate water-sharing disputes. Closed-loop systems, on the other hand, essentially just cycle the exact same water back and forth between 2 isolated basins, so they neatly bypass many of those severe regulatory and environmental snacks.
Let's move to our first major section, the execution reality, moving from geology to the grid. Because moving from a really cool concept on paper to the intense, gritty reality of building actual infrastructure, it's daunting. This timeline breaks down the journey of just one of these custom-built systems. Unlike battery storage, which you might deploy in, say, 12 to 18 months, PSH projects typically take a massive 6 to 10 years just to reach commissioning. First, you start with rigorous site surveys. Then you spend years bogged down in land acquisition and navigating clearances across multiple agencies. After all that comes the heavy civil works, literally excavating massive underground caverns and boring headrace tunnels through solid rock. It requires relentless execution discipline to ensure the project doesn't just stall out halfway through.
And because these projects are so wildly site-specific, the engineering geologists and geophysicists play an absolute make-or-break role. I mean, before a single shovel even hits the dirt, these experts are out there assessing the topographical viability, they have to mitigate severe seismic uncertainties, and deeply evaluate the rock mechanics. You have to be absolutely sure that when you hollow out a mountain for a deep-set power cavern, the whole thing doesn't just collapse on itself. Their mission is absolutely crucial. Even a tiny miscalculation in the geological assessment can lead to disastrous delays, massive cost overruns, or, worse, complete project failure.
Which brings us to the industry's hidden bottleneck. The unspoken reality here is that there's a severe shortage of the specialized, multidisciplinary teams capable of actually executing this vision. A single 1,000-megawatt project requires up to 3,000 personnel at peak construction. To meet that massive national target of 50 gigawatts, India is going to need over 200,000 professionals, engineers, geologists, commercial experts, project managers over the next 5 to 7 years. Currently, this level of integrated, project-ready talent is incredibly scarce. It's a critical soft infrastructure failure that absolutely has to be addressed.
Next up, we have funding the 50-gigawatt vision, massive investments, and M&A. Now, what's really interesting about this is how you pay for it. Building these massive assets requires intense capital, with upfront investments ranging from 40 to 70 million rupees per single megawatt. The sheer scale of the capital flowing into this sector is frankly staggering. Just look at these figures. Adani Green Energy is committing 60,000 crore rupees in Maharashtra alone. Torrent is planning up to 8 gigawatts with an investment of up to 35,000 crore. We're also seeing massive consolidation, like JSW Neo Energy's $1.47 billion acquisition. Plus, the government of India is stepping right up with over 12,000 crore in financial assistance to back these long-term bets. The corporate and governmental alignment here is practically unprecedented.
And the scope of these new investments perfectly matches the scale of the new projects. The median storage capability of future facilities completely dwarfs the existing fleet. The next wave of pumped storage is scaling up significantly in capacity, simply because modern grid demands, which are getting swamped by massive influxes of midday solar power, require far larger buckets to actually store that energy. This huge scale-up is exactly why those long-term capital instruments and sophisticated market mechanisms we just talked about are so crucial to de-risk these infrastructure bets.
But to actually get these giant projects built, states have to go way beyond basic tariffs. They have to build an enabling ecosystem. The state of Andhra Pradesh is really leading the way right now as the premier model for this. They're targeting 22 gigawatts by 2030, and they're pulling it off by providing strong budgetary support for essential infrastructure like roads and bridges, offering tax incentives, exempting land acquisition fees, and even eliminating upfront premiums. On top of that, they're allowing developers to monetize ancillary grid services, which completely shifts the commercial viability of these projects for the better.
So, what does this all mean? The crucial takeaway is this. India absolutely has the technical potential and the policy push to become a global leader in long-duration energy storage. But as we've seen today, meeting gigawatt targets on a piece of paper is only half the battle. The real benchmark of success is going to be whether the country can move beyond fragmented execution to build a truly resilient delivery ecosystem. It requires resolving some deep structural gaps in execution capability, market design, and above all, human capital. Can India build a specialized workforce and the institutional leadership necessary to execute this massive 50-gigawatt vision? Well, that's the multi-billion-dollar question that will ultimately define the future of its clean energy grid. Thank you so much for joining me for this explainer, and definitely keep your eyes on this fascinating sector.